This is week 3 of History of Industrial Design, the Industrial Revolution, in 2 parts. Part 1 is adding power to stuff. Part 2 will be how design was affected because of that. Usually when class is starting, I have these really great videos up on the screen. I'll link to them. If you're interested, go find them. They're really good. On the left, 100 Years of Railroad Development, a film from 1927, and on the right, the New York World's Fair in 1939, Railroads on Parade, a pageant of railroads with music improbably written by Kurt Weill. Both of these were made when the original engines still existed and could be filmed in use. Some of them now live in museums, some of them are gone. This was a moment when they were old, but not too old to still be used. So it's a great record of what these trains were like in motion. And the other movie is a silent film from 1923 called Our Hospitality, and it shows a replica of George Stephenson's rocket engine in use. The problem with this is it's a farce. All sorts of ridiculous things happen, but it still shows the train and the scale of things in a way that really helps bring it to life. So watch those if you're curious. Also, I want to mention, you can't talk about the Industrial Revolution and industrialization, especially not in a design history class, without also talking about the effects of that and what that led to. I don't want you to think I'm skipping the arts and crafts movement. I'm going to include that later. So today we're going to focus on the industrialization. As we looked at last week, industry began to produce wealth, and then as a result, social structures started changing. Power made production possible, and that power and progress enabled consumption, which eventually enabled everything else we think of as part of industrial design. So the first week I talked about a lot of things that I see in design, but were not actually design activities, engineering and problem solving. This week we're going to look at objects and technologies that seem more familiar to us because they have more parts of the puzzle in evidence. Also, if you're looking for the global narrative of design history, other weeks will offer that better than this week. We're mostly going to focus on Britain and on America because that's where industrialization is easier to study because it happened in a more concentrated way. That doesn't mean it's not still a global story because none of this progress could have happened without global resources, without colonies, without raw materials and cheap labor, which was usually enslaved labor, that fueled the advances and made the progress possible. So keep that in mind. We're going to look at England first because they had a lot of fuel, a lot of coal, and England was the only European country not devastated by the Napoleonic Wars, so they were ready to charge forward. We looked last week at America and all the water power and all the wood resources we had and the labor shortages and how that led to a need for more innovation. And the American system developed, but it took a long time to solidify and spread and be useful around the world. So we're going to look at America and England. That doesn't mean that there isn't a sort of shadow, and in this case a really ugly shadow, of other global stories happening. There are a couple of other reasons to mention for why globalization was concentrated. One would be measuring and tools. Specialized machinery was developed, and that allowed the making of regular machinery. Bolts and screws could be used to fasten things, and imagine how much more accurately you could start making things with the advent of screws. Screw making machines had been around for a while. They arrived in the 1760s, but there was no standardized thinking about screws. Each company made their own screw machine to make their own screws for their own equipment, so nothing could be shared. In the early 19th century, machinists and engineers like Henry Maudslay started approaching screw making as a standardized activity, so the same screws could be used in multiple places. It seems like a tiny detail, but it was a huge step forward in machining, which led to an even huger step forward in machine making and how machines could be used. Maudslay also introduced the surface plate, the metal lathe, and the advanced micrometer, so we have him to thank or blame for a lot of the industrial progress that happened at the time. The major narrative of this week is pretty simple. Iron plus power equals progress. If you take cast iron and add a power source to some pre-existing technology, combine a few technologies together, you get this exponential sort of change and progress. The story kind of begins with Abraham Darby the first. There were a few of them. In 1709, he figured out how to use coke, which is pre-baked coal, to allow hotter fires. And those hotter fires produce less sulfur, and that hotter fire with less sulfur allowed a different kind of iron to be produced. Darby was able to pioneer the smelting of iron ore that could be cast into thin sheets. So he could make a sheet material out of iron. He could also cast vessels with a thinner wall, with fewer air bubbles, with less cracking, and produce a lighter weight, more useful pot. He didn't invent the cast metal pot. We looked at ancient Chinese ones, but they were bronze, and bronze has always been quite expensive. As a result, they were highly decorated because they were ceremonial objects or for the royalty. In the early 1700s, Darby was able to use cast iron instead, which was a much more affordable material. As a result, sturdy, useful cast iron pots were available to many, many more people. And this is also where you start to see a complete lack of decoration, because this is a utilitarian object, not a ceremonial object. I happen to think they're beautiful, but you can agree that they're not decorated in any way. They're not designed. This is a painting from a few decades later of Coalbrookdale, Darby's factory. I looked at this painting for years and thought that the point of it was, look how bucolic and beautiful the landscape of England is, even with this factory in it. In fact, I was missing the whole point of this painting. In the foreground is a huge cylinder, which I mistook for a wagon. That is a steam boiler, a huge iron cylinder being transported by a team of horses, lots of horses. And that's the second reason the Industrial Revolution happened in a centralized way. The equipment that powered it was heavy. If you made a cast iron boiler in Shropshire, the part of England rich with coal, you were going to leave it somewhere near Shropshire because transporting it with bad roads and horsepower was really difficult and expensive. This is a painting of the iron bridge built at Coalbrookdale by Abraham Darby III, the grandson, that shows this engineering triumph, but it shows it in a really beautiful way, right? You want to go have a picnic or go boating underneath it. This shows the promise of industrialization, the progress that could happen. But there are alternative images that show a different point of view. These are two paintings from a little bit later that show Coalbrookdale in full swing. And people who wrote about the experience of encountering Coalbrookdale said that it was terrifying, belching smoke, the flames visible for miles. So industrialization had an ugly side as well. Cast iron opened the door to the new era. This is that bridge in a photograph today. It's still there, and it's an engineering triumph. Remember, this is not steel, it's cast iron, which does not have the same strength as steel. You couldn't make one long bar and span a distance. So it's made up of individual cast components that are then attached, bolted, or riveted together. This requires an engineering understanding of structure, of repeat parts, of how to build a large thing out of small things. And it's a real symbol for the dawn of this new era of new materials and also new engineering abilities. Iron was not new. It's one of our oldest metals. Wrought iron was not new. Wrought iron was produced in ancient China. We don't actually even know the date. It's so old. Cast iron was also not new. Cast iron happened in China as early as the 5th century BC. Even as late as the 1770s, in Diderot's encyclopedia, metalworking is a pretty modest enterprise. I don't know the actual title of this plate. I call it hitting metal. But you can see people are heating up metal in the forge. They're hammering it as a team enterprise. Someone's holding it, someone's hitting it. They're hitting it in rotations to keep the hitting happening faster than one human could do it. But it's still a hand effort. Even in the encyclopedia, there's evidence of it being scaled up with power. So off the screen behind me is a big water wheel turning that shaft. The shaft has 4 spikes, and when it rotates, those spikes lift the drop hammer, which is heavier than a person could hammer. So they're using water power to scale up metal smacking. But with the Industrial Revolution, things scaled up unimaginably from there. James Naismith introduced the steam hammer in 1832 using a steam engine to lift the hammer and then drop it. And because we could now cast iron, we get this huge cast iron frame that holds the steam hammer. On the right is a painting from the 1860s that shows an even bigger one, where now the worker isn't doing any of the hitting. Those little things on the left are people, and all they're doing is positioning the metal so the steam hammer can do all of the work. James Naismith was another early machinist who introduced a lot of progress, including forward, neutral, and reverse on a lathe, which anyone who's taken an advanced metalworking class will appreciate. He wrote that tools never got drunk. Their hands never shook from excess. They were never absent from work. They did not strike for wages. They were unfailing in their accuracy and regularity. Sounds like a fun guy, right? The first day, I showed you Herons Airlock, or wind ball. It was an early steam motor, a very simple one. The basic idea is the water's in the sphere, you add heat, which turns the liquid water to steam, and water expands when it turns to steam as it changes state, and that steam has to go out somewhere. By controlling the way it goes out, you create movement. It's a very simple idea, and it was a very ancient understanding. But we weren't able to harness that power and scale it up until we had better metal and better tools and more accuracy and the ability to make machines to house this ancient technology. I want to return to the Marley Machine, which I introduced briefly in that weird little talk on alternative power sources like animals. This was a huge wheel-based system in a river in France. The power of the stream turned the gears powered pumps, the pumps moved water up from the river to the fountains of Versailles. The reason I want to bring it back is, when you hear about this or see it, it seems ridiculous. Versailles spent more money getting water from the Seine for the fountains than on wine for all the people who lived there. It was a major, expensive undertaking, and it didn't really work well enough. So the French finance minister was regularly looking for a way to replace this thing to save money, but also to perform the act of moving water to the fountains better. Christian Huygens, the famous Dutch engineer and scientist who discovered Saturn's moons, who developed the pendulum, who discovered centrifugal force, who discovered wave theory of light, lots of things, smart person, was brought in to see if there was a way to improve the Marley Machine or replace it. I want to just insert that here because everything we look at for the next 2 weeks will be based on this foundation, which seems impossible, but is true. He spent 7 years investigating a pretty simple idea, using a small amount of explosives in a sealed container to create a vacuum. He invented something that was called the gunpowder engine or explosion engine. We call it the Huygens engine. And this is the only image of it that I believe exists. On the left is a reprint of it from the 1880s that was cleaned up. And I thought it must be just badly drawn because the cylinder is 8 feet tall. And those little teeny people are supposed to be 8 boys who were lifted into the air by the power of this explosion. So the scale's all wrong. And I was blaming the artist from the 1880s. But last night I found in the Bibliothèque Nationale in France a scanned version of the original publication, and it's the same drawing, only a little bit worse even. So the scale's wrong, but the idea worked. I mention this because Denis Papin, who was a Frenchman working to assist Huygens, then took this work to England and developed it further. And his change was to replace explosion with steam power, the changing state of water expanding instead of exploding gunpowder. He also, in the process, invented something that turned into our modern-day pressure cooker, and that's the thing on the left. So there are a few reasons to like him as well. I'm going to revisit this story of explosive power next week because you really won't believe how much of our world goes back to this story. But for the purposes of this week, Thomas Savery was a British engineer who developed something called the miner's friend. He was trying to figure out how to use steam power and atmospheric pressure. So as the steam cools, you could use the vacuum that's created to pull water out of a mine. Because one of the problems with industrialization was we needed more coal to make more cast iron. Making more cast iron allowed us to have steam power, which needed more coal to fuel that. We needed more coal. The deeper you dig in your coal mine, the more water fills up. So this is a self-perpetuating cycle. We need more coal, we have to dig deeper. We need power to move the water out of the mine to get more coal. And at the time, water was removed from mines with buckets. So there was a real race to figure out how to keep mines dry through some mechanical means. Savery's device didn't end up working because atmospheric pressure wasn't strong enough to pull water out of a mine, but it got people thinking about this idea of using a pump. And then we go back to Denis Papin, who was back in Germany at this point, working with Gottfried Leibniz, and he combined some of this thinking, the piston and the condensation, to make the first steam engine. And they used it, of course, to power a boat. Why would you power a boat? Think about it. Boats pre-existed. You didn't have to invent a new thing. Anything on land needed wheels and parts and had resistance. Boats have less resistance in the water, so it just made perfect sense to just dump a steam engine in an existing hull and see what happened. We have no images of it, so I have some schematics of the engine, but I have no image of the boat. The only images that exist were made much later, and they illustrate a funny moment where the boat was destroyed by ferrymen who saw the end of their labor in sight and wanted to prevent that from happening. And the images are sensational, so there was just no reason to include them. Historically, none of what I just said matters. You didn't even have to listen to it. There is no quiz. Because we know that Thomas Newcomen invented steam power. That's the story. He didn't invent it, but he did make it practical and useful. He attached steam power to mining in a way that really helped. Newcomen created a steam engine in 1712 that was used to pump water out of mines. 6,000 gallons of water a day had been taken out by buckets, by people with buckets. So think of all that labor that's saved if you just have a machine that does that for you. It's also portable. I know you're going to look at this image and laugh. There's nothing portable about that by our standards. But if you think about the Marley Machine, which was in the river, you needed to move what you were working on to the power source, always, since the dawn of time. Suddenly you could move a power source to where you needed it. So that's what I mean by portable. You could erect it where you needed it. It's just some bricks and wood. But this machine was not especially efficient, because notice that the piston goes up when there's steam pressure and down as the steam turns back to water and it cools. That same chamber needed to cool off between every stroke, so it wasted huge amounts of energy. Also, the Newcomen engine went up and down, which is convenient for a pump, but not so convenient as a power source for rotational things. So the next development in steam power was to make a rotational system where the power from the steam engine could be constant and hooked up to things. James Watt was part of this story. He patented his design, which also included 2 chambers. So instead of one getting hot and cold, one stays hot, one stays cold, and the contents are transferred in between. That was a huge savings of energy and increased efficiency. In the process of figuring this out, he also discovered the chemical composition of water, which is pretty exciting. Look at that engine on the left. It is a huge iron structure. So again, without iron, we couldn't have had the machines that powered this era. I have one more slide to show you for this era of steam power, because there was already an existing patent for turning linear motion into rotational motion. So rather than pay that person for their innovation, Watt set about to invent his own method, which turned into the sun and planet gears, this beautiful sort of mechanical constellation of rotational ballet. And I know none of these videos on their own really helps you appreciate that or understand it, but maybe all 3 together will. I also wanted to show you a sense of scale. The Powerhouse Museum in Australia owns the one on the upper left, and in operation, in its space, I think you can really get a sense of how vast this equipment was. Imagine all the things that can be improved with power sources. If you needed to drive pilings for marine applications, you had to put horses on a float, get them out, make them walk around to power your hammer, dropping over and over again. They need food, they need rest, you have to get them back to land at the end of the day. With steam power, you just get a steam engine out there and it can go all day, all night, as long as you want. You can leave it there and row to shore. Huge improvements in lots of areas. I want to go through a few disciplines or areas of progress to show you how this equation of existing technology plus steam power equals a new thing and how that played out. And the first chapter has to be transportation. We started to take charge of transforming the landscape in a much more invasive and major way than we ever had before. We wanted to get more stuff where we needed it faster. We built roads, we built infrastructure. This image shows you why we might need that. This is someone moving coal on a track. It's not really a train, it's a track for his cart. And the horse has pulled that cart up the hill, and now at the top of the hill, the horse has moved behind the cart. That's where the expression putting your cart before your horse comes from. And the driver has a really optimistic hand lever for a brake. And I think you can imagine what might happen next. Chaos. It didn't take people very long to realize that you could have a steam chamber powering rotational movement, stationary to power equipment, or you could tip it on its side and let that rotational movement move the actual engine somewhere. You could have moving power. Here's some information to think about. We walk at about 4 miles an hour. A horse walks at about 4 miles an hour. It can go 8 to 10 trotting, and it can go up to 30 galloping, but it can only do that for limited amounts of time. So for centuries, our whole time on the planet, if you wanted to take a long distance trip, 4 miles an hour. When George Stephenson's active engine pulled the first passenger train with 450 passengers, it went 15 miles an hour. And just a few years later, 4 years later, the rocket engine went 36 miles an hour. Imagine living in a 4 mile an hour world and suddenly being welcomed into a 36 mile an hour world. I know what you're thinking. You've been on the road behind someone driving 36 miles an hour and you want to explode with frustration. But think of the advance. Also, look at the passenger cart in the upper left. It was not a well-developed system, but it was an exciting new one. Also, it would go as long as you had tracks and fuel. Again, you didn't need to stop to sleep or rest. Stephenson wins the prize of getting credit for this practical steam train, and today's talk is all this person gets credit, but this person did the work. Lots of people were working on the same innovation at the same time. John Stevens, who was father of America's patent law, was an advocate for steam power in America, and he was so excited about this that he built a track around his property in Hoboken so people could see a steam train in action and get on board. And his second train, the Bull train, introduced in 1834, was put into service and still exists. It's at the Smithsonian in Washington, and it's a pretty awesome thing to encounter. The era of train travel and transportation was ready to start. The first common carrier passenger train in the United States was the Baltimore and Ohio, put into service in 1828. And this is its engine. It has a vertical boiler instead of a horizontal one. I'm really intrigued at the difference between a machine and the human interface part of any design system. This is the machine. We don't care what it looks like. We want it to look powerful and sturdy, and it does. But what was attached to it tells a different story. In 1828, no one knew what a train was supposed to look like. What should a train be? So when you have new technology, there are only two possible answers. One is invent the future, make it new. That's a liability because most people will be afraid of that or unwilling to embrace it or invest in it. The other option is to make it look old and familiar. Don't worry about this new thing called a train. It's just like the carriage you already own, just linked together. So the first passenger compartments of trains were carriages attached to that steam engine. And I think they're hilarious and stupid and wonderful and beautiful. It also makes sense because no one knew how to make a train. So what you do when you're inventing something new is look at the next closest adjacent technology. We had a long history of making carriages. Carriage makers knew leaf springs and how to absorb motion and which way to face people so that they could absorb that motion with their legs while sitting down, how to cram as many people in as possible. There was already a lot of shared knowledge that could be appropriated for train building. Almost all the early trains told the same story in America, in England, all over. I love the picture in the upper right, which is a British train car from 1834, so the same time period, just a little bit later, but really quickly we figured out it would be more cost effective to make one compartment that more people fit in. And yet they painted carriages, 3 carriages on the side, so that you'd still know what this was. They signified this is not a new thing, this is that thing you already knew all about. Railroads quickly took over in America, in England. This is a map of the eastern seaboard of the United States. On the left is 1850, on the right is 1860, so 10 years. We started with some small rail lines that mostly were privately owned to get your goods from your factory to the dock. And they started to get interconnected and turn into a network. Same thing happens in England. 1851 to 1881, there is a real multiplying effect of rail. And you can see that they're going from ports to inland cities. This is a famous image for a lot of reasons. 1869, Promontory Point, Utah, where the train line from the East Coast and the train line from the West Coast met. And the celebration is that we could cross the continent by train in only 6 days, which sounds slow, but if you think about doing it in a carriage, which would take weeks, it was a huge advance. One of the many reasons this photograph is now famous is for what's not in it. Over 20,000 Chinese immigrants built that train line, did all the hard manual labor to get that train to happen. In this picture, there was only one Chinese worker. You know, that's the story of the day, all the people who did the work and the people we're remembering for it. Rail development allowed a lot of other things to develop as well, technologies and infrastructure. When we built the train lines, we also installed telegraph lines. They have a long relationship, first as one service and then splitting off, and then later we could add telephone lines along those existing poles. This is one of the problems in America. We built our train lines and then built right up to them in the most congested parts of our country. So we have very old, slow trains because we can't replace those lines. That shared long-term infrastructure was a triumph at the time and is now a problem for us. I also want to point out these are 3 subsequent designs for a telegraph machine, and I love seeing the advance of the form in a new technology. The first one is just wood, and you push down with your finger and it makes a metal contact and it makes a signal through the telegraph. We didn't care what it looked like, it sent the message. But really quickly, the people who had to use this all day started to complain, right? There's nowhere good for my finger. There's too much resistance. Whatever their feedback was, the next one incorporates. There's a concave area for the finger. It's got adjustable sort of spring response so that you can trigger more quickly with less resistance. And on the right, the third version has bells and whistles and a wooden cabinet and polished brass. That's usually how technology advances. There's the sort of steps 1, 2, and then 3. We arrive at a product type. Think about all the things that trains are going to require. Trains don't like to go up a hill, trains won't go through water. So we had to figure out, if we wanted our trains to be a long network, how to get across a gorge, how to get across a river, how to get under a mountain or under a river. Tunnels and bridges, as a new engineering feat, are the triumph of the era. Isambard Kingdom Brunel is probably the greatest of the early engineers taking this challenge on. Designers identify a problem and then explore solutions to that problem. Engineers tend to work in a different way. They'll find a structure and scale it up and look for applications for that structure. We'll look at a few of those this semester. Buckminster Fuller's a great example later. Brunel did that. He found these wonderful mechanical engineered structures and scaled them up to span huge expanses to get trains across rivers. I think as a result, they end up being as beautiful as they are useful. The Brunel family changed a lot in our world. His father, Mark Brunel, lived in America for a while. He actually submitted a proposal for the Erie Canal, which was not chosen. But while here, he looked at some of the advances in thinking about repeatability in manufacturing, took those back to England and really supercharged them. He produced all the custom equipment that made the Portsmouth blocks. There was a need for thousands and thousands of blocks for the shipping industry, and he produced sequential machines that turned a block of wood, actually a tree, into a block with automated steps. He also began, and then his son Isambard completed, the Thames Tunnel, which was another engineering triumph, tunneling under the Thames for pedestrians and horses so that the shipping industry could own the river above undisturbed. You can still see this tunnel. It was incorporated into the tube system. So if you know where to sit and look out the window at the right time, you can see it. Train advances also allowed a complete change in commerce. I'm skipping ahead a little with this image. This is the Sears and Roebuck catalog from 1889 and 1903. We're going to look more at that next week in the Art Nouveau period. But think about what would change with longer distribution systems. This is very much like what the American peddler did by filling up his cart with goods and taking them west from urban centers, but magnified. If you had a warehouse and you received mail orders and you filled the orders, you were sitting on a lot of inventory. And if people didn't want the stuff you had, you were really in trouble. So what we start to see is not only what we saw with the American peddler, which is changing the design of objects so that they would transcend regional preference, but we start to see predicting styles and even more controlling the next style that will be popular. That's something we do now. There's style forecasters, and that helps people make stuff in advance of next season. That's something that goes back to the advent of trains and the distribution systems that they enabled. We cannot talk about the Industrial Revolution without looking at textiles. The changes in the textile industry were complete, but they also changed everything about global economics and politics and morality. Weaving is ancient. It may well be the second oldest profession. But even as late as Diderot in the 1770s, weaving was relatively similar to how it had been done for centuries. The width of our fabric was controlled by our wingspan, by how long our arms were. You have to pass the shuttle back and forth across the weft. So on a small loom, you can do that yourself. On a wider loom, you need someone on either side pushing with a stick. Our fabric was constrained by that limitation. Weaving was a cumbersome, difficult activity the whole time we were doing it. The Industrial Revolution offered a series of small incremental steps forward that each took existing technology and added power or changed a mechanism to completely transform the process of weaving. The first step forward was adding wheels to the bottom of the shuttle and putting a support underneath the warp so you could roll it across. The flying shuttle allowed one person to weave much wider, much faster than had ever been possible. It seems like such an obvious idea that it should have happened long before, but that's what happens with innovation. An obvious idea suddenly enters the stream and unleashes a whole bunch of subsequent steps forward. It's difficult to describe it with language what a flying shuttle does in action, so I'm including 2 videos so that you can see there's a box on either side that the shuttle flies back and forth between. They're connected by rope and a handle, so the operator moves that rope back and forth and smacks the shuttle back and forth. It cannot be good for the arm or shoulder or elbow of that person doing the work, but look how fast they can weave. If you're interested, you might want to check out the Burroughs Garrett, Justin Squizzero's work on the bottom video there, because he has a hand loom, flying shuttle loom, a jacquard loom, and is using them all in today's world to keep alive these older weaving techniques, which at the time I'm talking about were brand new. If you add to that this new idea of continuous power, you get real progress. If you take the flying shuttle and instead of moving it back and forth by hand, use water power or steam power to smack it back and forth and to operate all the other parts of the loom, you're going to get fast fabric, you're going to get more regular fabric, you're going to get tighter weave, fabric will change. This improved ability to weave led to a dramatic increase in the demand for cotton. The cotton trade between the United States and England exploded. In 1830, we were shipping 700,000 bales of cotton to England, and by 1860, over 5 million. That crazy increase created a really complicated relationship between England and America and the rest of the world as well. To give you a sense of what could be produced with all this cotton, 1 acre of farmland can produce 1.5 bales of cotton each season. 1 bale of cotton weighs 500 pounds. 1 bale of cotton makes 1,200 t-shirts, to put it in some terms we can understand, or 313,000 $100 bills, a term I can't understand. So we needed a lot of farming to meet that demand. Cotton had been used for a very long time, as early as 12,000 BC in Egypt, but about 3,000 BC around the rest of the world. There is a variety of types of cotton plants, and they like to grow in different parts of the world in different climates, and that's part of the problem in this equation. Cotton plants with long fibers grow in tropical climates. You want longer fibers because the fibers are attached to a seed, and you have to manually remove the seed. So that's labor, and the longer that fiber, the less labor. Also, the longer the fiber, the easier it is to make thread out of it, less twisting, less bundling. Remember that nature didn't make cotton so you could have a t-shirt. Nature made cotton so that those fibers could work as a parachute to get the seed as far away from the plant as possible and procreate, make new cotton plants. The goal nature had in mind for that fiber was to stay completely attached to that seed the whole time. Our goal for t-shirt making is to separate them as easily as possible. So if we're going to use shorter staple cotton, we have more seeds to remove and there's more labor involved. Unfortunately for the textile industry, the cotton that could grow in the American South was short staple cotton. So we needed a lot of hand labor to separate the fibers from the seeds. The United States went in this time period from being a colonial agricultural economy to being the second biggest industrial power in the world, solely on the basis of the success with cotton. There are 2 crucial components to the landscape that allowed America to achieve this success. The first is enslaved labor. The inexpensive labor of slavery changed the economics of farming. And when you think about it, free labor, enslaved labor, is only inexpensive financially. It's the most expensive labor morally, historically. The repercussions of those decisions are still with us today, right? That's one of today's biggest struggles, still. Remember that industrialization does not remove human labor. It amplifies it and concentrates it. It moves it somewhere you can't see it anymore. And that's true in today's world as well. The 12,000 t-shirts made with a bale of cotton are being made by a modern day version of slave labor. There's someone who's perhaps you can say being paid, but not a living wage, not living in circumstances that allow them other options. That's a kind of economic slavery. So we still very much have the price tag of industrialization as part of what we're supposed to be struggling with and making progress about. There are a couple of other things to think about. American farmers were relatively new at this idea of warm climate farming. We had only been doing it for a couple of generations. We didn't know how to grow short staple cotton in the South, but the imported enslaved labor was part of cultures that had centuries of farming expertise. The shared knowledge of how to farm in a warm weather climate that came with the enslaved workers is what made this system possible. So keep all of this in mind for the entire rest of the semester, because everything we're going to talk about in manufacturing and industrialization needs raw materials. Raw materials and labor will always involve inequities and unfairness. The second thing we needed to happen to make this explosion of cotton productivity was finding more efficient ways to separate the grain from the fiber. Because we were using short staple cotton, we had to do a lot more of that. By hand, it's a lot of work. Every pound of fiber collected has 3 pounds of seeds that were removed from it. So anyone who figured out a way to do that would increase output. One cotton gin, which is an engine for cotton production, that's why it's a gin, it's an engine, could do the work of 50 hand laborers. And it's a very simple device. The first one had a wooden cylinder with grooves and metal fingers that fit in those grooves, and they just raked the cotton. They raked the seeds out of the cotton. The cotton fibers go out the end, they're blown out the end, and the seeds fall down below. I'm showing you this really clumsy, stupid video for a couple of reasons, because it's funny. We need some humor at the moment. 2, it shows this in operation in a way that's really easy to understand. And 3, it shows you the scale of the object. But no, a farmer would not be operating this with his beautiful wig on his head. We're told that Eli Whitney gets credit for this invention, but come on. He was a Yalie. He went to Yale. He was from the Northeast. He was invited south by a classmate of his from Yale named Phineas Miller to help develop this idea. So the idea pre-existed before Whitney came on board. So these are 2 guys from New England who didn't know anything about cotton farming, who suddenly in a couple of weeks or a month invented this world-changing device. It's a little bit difficult to believe because Whitney was pretty much an outsider to every body of knowledge involved in this story. The enslaved laborers had already been using metal combs as a raking process to remove the seeds. It's not a big leap to make that a rotational movement instead. It's possible that Whitney introduced that, but he can't be responsible for the entire chapter. So Whitney gets credit for this innovation in history, but it didn't get him much more in his life. It was impossible for him to profit off of this for 2 reasons. 1, if you look at it, it's just wood, a couple of metal parts. Most people had a way to make a version of this themselves. Why would they buy one? Why would they pay him for it? We had a young patent system. This is patent number 72. So it wasn't as enforceable as patents became later. But the bigger reason is that only 4 years later, someone made a newer version that worked better. Instead of metal combs, it had blades, rotational blades. And in fact, as an aside, because I know you live for asides and longer lectures, the patent image on the lower left is patent X72. It has an X in the number because the patent office burned down and all of the paper patents were lost. We had some of the models that survived, but the paper patents were lost. They were reproduced from memory, from copies the inventors had. And this drawing of Whitney's gin is actually inaccurate. If you look closely on the left, you can see 3 circles, 3 discs. Those are the blades that cut the cotton. That's the way every cotton gin, when this was redrawn, worked. So no one in the office producing this drawing could conceive of a different way that the cotton gin had worked before. So this is Whitney's original patent, but it's not actually for his original design. I find that interesting and worth telling you. Again, if you add cast iron and power, you change the equation. Imagine how much faster ginning could be if you added a treadmill with a horse on it. Imagine how much faster that could be if you used steam power instead of a horse. Every other aspect of the textile industry got re-examined and reimagined and expanded and scaled up in the Industrial Revolution. This is what I call a junk slide. There's images on it that kind of relate to what I'm saying, but not that closely. The point is, spinning wheels are old. We had made thread by hand for a very long time, since 18,000 BC, with spindle whorls and other methods. The spinning wheel was introduced probably in India around 500, but everyone around the world adapted this quickly after. It really changed how we made thread, and that's how we did it from 500 on. In the Industrial Revolution, even this got re-examined. If you take that one rotational movement and expand it and do 8 at once, you have 1 power source and 8 outcomes. You've increased the amount of thread you can make. Pretty quickly after that, that got scaled up to 80 threads at a time. Before 1764, 500,000 pounds of cotton was spun every year in England by hand. By 1785, which is only 11 years later, 16 million pounds of cotton a year was being turned into thread. So there was a huge increase in thread production, and as a result, a huge decrease in the cost of thread and fabric you made from the thread. And then if you add a power source, you can not only increase the output, but improve it. This is Arkwright's water frame, which uses a water power source, that's why it's called water frame, to make thread. And what that's going to do is pull out the thread in a more even way and twist the thread more evenly and tightly than you could by hand. So if you've ever seen handmade thread, it's irregular, it's bumpy in places and thinner in others. It also tends to pull apart in places and be stronger in other places. This is a much more even, reliable, and strong thread. He didn't invent any of this. Arkwright stole everyone else's idea and just combined them. He got very, very wealthy. He started out as a barber. He ended up as someone with 500,000 pounds. That's over $300 million today. And that's all based on making better thread. If you add all the parts of how thread could be made together and scale that up, you get a pretty dramatic increase again. If you take the spinning jenny plus the water wheel plus cast iron, you get this incredible image. This is a view from 1830, but it's of a Crompton spinning wheel. And you can see that not only do we have a huge piece of equipment, it's the entire length of this building making all that thread at once, but we get some other stuff in this picture that we haven't known before. We have cast iron trusses, because this building needs to have no columns so the machine can operate. So we get a whole new kind of architecture to allow that manufacturing, and that's possible because of the iron. We also get women working in factories. That's a new thing. We get children working in factories. They're tiny, they fit under equipment. They have small fingers that can pass thread through a small opening well. This is called a mule because it's a hybrid of two things. This is an industrial mashup based on a natural mashup where you take a horse and a donkey and make a mule. A mule is half horse, half donkey, and mules can't procreate. So you always need a horse and a donkey to make a mule. Why am I telling you this? I can't stop myself. This is a view on the left of an actual Crompton mule from the time still in operation. And on the right, 100 years later, a Birmingham factory that made thread the same way. This is how we made thread for a very long time. I don't know if the breeze blowing my green curtain is affecting things. The power loom arrived at the same time, 1784 at first, but not in a usable way, and then in the 1830s in a more usable way. Imagine what happens with this perfect storm of combinations. Lots of cotton, perfect threads, tightly woven on a power loom, really wide. You're going to have a complete change in what fabric is in our world. Also, printing was changing. On the left is block printing of wallpaper. That's using technology that's very ancient. Ancient Chinese, multiple wood blocks. You ink each one with a separate color. You line them up carefully and you get a complex multicolored pattern. But you can see how slow this would be. Every block has to be re-inked and carefully positioned. The paper has to dry before the next one can be applied. On the right is roller printing wallpaper, where a rotational drum with artwork etched on it rolls in a trough of pigment and transfers that pigment onto the paper. With better chemistry and fast-drying pigment, you can do multiple colors sequentially and have one finished product at the end of the process, as long as you want. When you change fabric to be so regular that it's like paper, you can also then roller print onto fabric. For centuries, patterned fabric was the most expensive kind because it had to be hand-woven or hand-embroidered or hand-printed. Suddenly, yards and yards of intricate, colorful cotton is being printed. Calico cotton was invented and completely changed what fabric meant. Also at this time, we got the chemist trade beginning, so you could buy bleach, you could buy mordants, you could buy alkali, you could buy better soaps, instead of having to make it all yourself. And that allowed manufacturers to scale up what they were doing as well. The last piece of the puzzle in textile advances would be sewing. For centuries, we sewed with a needle by hand, back and forth through the fabric, making a series of stitches. Elias Howe arrived. He didn't invent the sewing machine. People had been working on it beforehand. What he did introduce was two separate threads on each side of the fabric that pass through and create a lock stitch. So this is the device he made that does that. You turn the crank by hand. The needle on the other side goes in and out of the fabric. You have to hold your fabric vertically and move it while you stitch. This is not a machine that's easy to use, or I would argue even useful. But that lock stitch was a really important step forward. He patented this. He was not able to commercialize it because I think this is a bad design. It's good engineering, but bad design. So if you ask most people who invented the sewing machine, they're going to say Singer sewing machine. That's also not true. Lots of other people had come before. Elias Howe introduced the sort of central technology that everyone else then used, including Singer. A lot of people feel bad for Elias Howe because he's not remembered by history. He made out fine. He sued everyone who infringed on his patent. He eventually won those cases, and he ended up getting $25 for every sewing machine anyone else sold that used his lock-stitch innovation. Motorcycle brake. In fact, Singer had almost nothing to do with the technological advances of sewing machines. His big patent of 1851 is for a cam mechanism that turns the rotational movement of the shaft into an up and down movement for the needle and the presser foot. That's it. But the other innovations he introduced completely transformed what a sewing machine could be and how it became available to us. He rotated the work surface and created a table for us to work on. He added a foot treadle so that we could power it with our feet and steer it with our hands. Just those changes are enough. They made the sewing machine useful. He also realized that this was a heavy cast iron object that needed to be transported in a crate. The picture on the upper left shows the crate. You take your sewing machine out and bolt it to the top of the crate, and then you have a foot treadle built in. So the packaging becomes part of the object in use. The real progress in sewing machine manufacturing did not come from manufacturing or engineering. It came from a legal action. Because no one person owned enough patents covering the technology and mechanisms inside a sewing machine to be able to make a functioning sewing machine. Anyone making a sewing machine was infringing on someone's patent or paying someone else to use their technology. So 9 different patents were pooled together in something we call the Patent Pool of 1856, or the Great Sewing Machine Combination. Those 9 patents allowed people to make functioning sewing machines. So instead of having to pay each person separately, someone who wanted to make a sewing machine could just pay this consortium a fee. It was $15 to then use those patents to make a sewing machine. Now you might wonder, if Howe was getting $25 for every sewing machine Singer made, why would he settle for the $5 that he got of that 15? It was because they were able to sell so many more licenses as a combined pooling. So this is a really interesting legal precedent for sharing technology inside the patent system. Howe ended up making over $2 million off of this arrangement, in his day dollars, not in converted dollars. So he did pretty well. The reason Singer is known as the person who invented the sewing machine, or the enduring name in sewing machine manufacturing, is the marketing. He wrote, "To ensure success, only 2 things are required. First, to have the best machines, and second, to let the public know it." I would argue they didn't even make the best machines, but he proclaimed that so loudly and in so many places that people had no choice but to believe him. But there's a lot that marketing savvy introduced to the world, and we should look at that. First, he realized very quickly that that wooden base, although practical and useful and money-saving, was not going to work in people's houses. The photograph on the left is a really early photograph from 1851 that was used to advertise the sewing machines, and you can see right away that that base has no place in this woman's beautiful parlor with its beautiful wallpaper and her beautiful clothing and the beautiful rug and this piece of industrial equipment. Really quickly, Singer realized that the equipment needed to match the decor, and sewing machines became available in a wide range of styles so that you could suit your own taste. You could use it in industry in a factory, or in your sewing room with your Japanese screen and your animal carpet. Singer realized that style would matter. What the thing looked like made a difference and would get this into more places. Also, just notice in the upper left, there's plywood being used for the case, and there's plywood being used for the sewing machine tables. We'll look at that when we look at plywood way later in the semester, because Singer was one of the biggest users of plywood at the time and part of the early development of plywood as a technology, as a material. Singer also, and I should point out he had business partners, it's not just one person's brain, but Singer pioneered the use of what they called installment purchasing plans. We would call it a payment plan. And this is a kind of really early service design. He realized that people who could make money with this sewing machine, people who would want this sewing machine, couldn't afford it. A wealthy person could afford it, but they don't make their own clothes. A poorer person who might be a seamstress or a tailor or take in sewing for other people couldn't afford it. So by letting them pay a little bit each week, it let them buy the equipment as they earned income by using it. It also allowed Singer to charge them more for it. Instead of selling it for its fixed price, He could just give a weekly amount, and people could afford the weekly amount and didn't usually do the math to see how much more they were then paying. That's the foundation of our entire world now. You buy your car, your house, your refrigerator, all sorts of things on a payment plan so that you can have the benefit of owning it before you actually can afford it. And the people who finance that are making a lot of money off of you. So Singer gets credit for that. Thanks, Singer. Singer's sales doubled between 1874 and 1880. And then they doubled again between 1880 and 1886. So that's why he gets credit for inventing the sewing machine. He made more of them than anyone else. He sold more of them. He advertised more. He left more of a paper trail of his activities. He died in 1875 with an estate worth $14 million. In today's dollars, that'd be about $300 million. Also, Singer was one of the first multinational global corporations. Why would you make a heavy cast iron thing in America and ship it to Ireland if you could make it in Ireland or India or anywhere else? And as a result, because there was no Facebook relationship status or internet or WhatsApp or way to call France, he had a couple of other things. In addition to factories around the world, he died with 4 living wives and 18 children. He had no moral compass. This guy was a sleazeball. I want someone to make a movie about this. It would be so interesting. This is a quick side note. I'm not allowed to talk about fashion history because 1, I don't know anything about it. 2, that's not what this class is. But think about the cause and effect of all of this. If for centuries you defined your status in the world through your clothing, and the more decoration you had, and the more fabric you used, the wealthier you were, and people who worked for you couldn't afford to have all that fabric or any patterns, suddenly anybody can buy insanely beautiful, colorful, highly detailed, very fine fabrics. How do you define your status in the world? If you can't define who you are through the quality of your fabric anymore, you can define who you are through the volume of fabric you use. So part of the reason that clothing became more voluminous in the 1830s, 40s, and 50s, big sleeves, big collars, big skirts, was a way to consume more fabric and maintain your status in a way that signified visually. My last example of how iron plus power changed things is to look at food supply, because that also scaled up. All of this is in the textbooks that are available to use with this class, so I hope my students are going to be looking at those. I'm going to talk through this fast because to go through all the innovations and the people involved would take some time and not help augment the bigger story, which is actually pretty short. Farming techniques like textiles were really ancient. As long as we've been around, we've been farming. And they hadn't changed a lot over time. When you grow wheat, you have to remove it from the earth, and then you have to separate the chaff from the grain, the stem from the seed. When mechanical devices started to do that for us, we could farm on a larger scale. In 1834, Richard McCormick developed a mechanical reaper, a way of cutting the wheat down mechanically with rotating paddles. His son Cyrus McCormick, who was not the inventor but was really good at business, figured out how to patent it and how to monetize it. He turned this into a huge, huge business. Ancient Romans had reaping machines, but nothing like this with gears and rotating paddles. So the horse pulls the machine. That motion turns the wheels on the machine, which activate gears that rotate paddles. Those paddles cut the wheat, and it piles up on a platen, and the farmer rakes it off. Later versions also separated it and bundled it. So there were lots of incremental advances just in this one piece of equipment. We're going to look at this again in the second part when we talk about how innovation led to design, because there's a great story about what this did when it traveled to London. The same progress happened with all parts of the farming process, how you grow and process food. In ancient Egypt, grain was winnowed. The chaff and the grain were removed. The seed and the stem were separated by throwing it in the air and catching it. So just using mechanical effort and air did that. And we did it that way for a long time in the rest of the world, a really long time. In China, starting around 200 BC, there was a much better mechanical option called the rotary winnowing fan. So you dump your grain into a hopper, you turn the crank, and paddles inside aerate the grain and force that separation to happen faster. With a winnowing fan, you can produce 99 pounds of grain an hour instead of the few barrels of grain a day you could do by hand. So there is evidence of farming improvement that's really old, but if you power that up with horses, have horses walk around turning iron gears, mechanically separating the grain and the chaff, and then the grain goes one way and the chaff goes another, and you're all done. That changed the volume possible with farming in an amazing way, because the bottleneck had not been nature growing stuff. The bottleneck had been human power to harvest, to plant and harvest. And then again, if you add steam power, if you have a steam engine in the farm field, you can attach that and do even more. With the case mechanical thresher, you could process 200 to 300 bushels a day, huge amounts of grain. We're going to look at this more in the Art Nouveau period, because we see that food starts to become a manufactured commodity, and then it needs to be packaged and sold, and there's commerce and marketing. So we're going to look at that again. I just wanted to point out that every aspect of how we lived got scaled up because of steam power and iron. So that was a funny kind of smattering of information. Maybe not as clear or compelling as I would like, but I want you to consider how monumental these changes were. In technology and manufacturing and in marketing and in commerce, sure, but also in global trade and all the global entanglements that come with that, all the complexities of industrialization that we're still stuck trying to figure out. Think about material use and how combining innovations leads to progress. We still have so much to learn about that. We think that we need to design new solutions. We don't. We need to find out how to apply existing solutions in better ways, in more innovative ways. I think that the Industrial Revolution has a lot to teach us about how we could be solving problems better today. So take a break, come back for the next chapter, which is looking at how design arrived to deal with all of this. If you're going to make more stuff, and if you're going to make it there, but think about it over there, design has to happen in between to negotiate that. See you soon. This is my second time recording this because something went wrong with the audio, so let's hope it goes smoothly. I have to stand with my feet out because the back of my sneakers are green and they'll disappear otherwise. My glasses are so dirty. I have to move because the floor is creaking and it's driving me crazy. I think my glasses are crooked, or maybe my head is crooked. Oh, my feet hurt. Oh, it's very, very, very hot. It's very, very hot. Can I just open this window? Can I open this window? Oh boy. Oh boy. I'm sweating. I'm so hot. What can I do about it? I can't turn the fan on. I just have to endure it. I can't believe it. This is my life. I cannot believe this is my life. You just want to think your life's going to be fun, and then this happens. Okay, whatever. That crazy increase created a really complicated... I can't have the window open. I want to be finished!